Hello students. Before we begin with today's class, let us recall some concepts that we have done in our last lesson. We have seen that true solution and suspension. These are two extreme categories of mixture and in between them exist colloids. Colloids are homogeneous looking heterogeneous substances. Now what makes the colloid particles interesting ones? That they are charged particles. All particles of colloid will have same type of charge on them, either positive or negative, and this charge is responsible for the stability of colloid. About that we'll study in detail in the next upcoming video, but right now we have to remember that colloids are the charged particles. So today we will study about the preparation of colloids and the properties of colloids. So let us begin with the preparation methods. The very first and the simplest method is chemical methods. By using variety of reactions like double decomposition, oxidation, reduction or hydrolysis, we can prepare different type of colloids or different type of sol. Now whether I say colloid or whether I say sol, it is one and the same thing. Let us begin with the first example. Arsenic oxide when treated with hydrogen sulfide gives sol of arsenic sulfide. How does this sol is obtained? Now when this reaction is carried out, we get the precipitate of arsenic sulfide. Okay, that is a sure thing. Now this precipitate of arsenic sulfide, it will have charges adsorbed of S2 minus. Now from where S2 minus will come? From H2S. So there will be some S2S minus particles in H2S. They will be adsorbed on the PPT of S2S3 arsenic sulfide. As there will be charges on the PPT, it will be converted into sol. Similarly, if we look at this reaction, AuCl3 plus methanol giving the sol of gold. Now what happens in this case? The methanol act as a reducing agent and itself get oxidized to methanoic acid, and AuCl3 gets converted to sol of gold. Coming to the next example, FeCl3 plus 3H2O will give the sol of FeOH3. Initially, we get the precipitate of ferric hydroxide. Now this ferric hydroxide precipitate, it will absorb some of Fe plus 2 from FeCl3, and as a result now it will get converted into sol. How the precipitate gets converted into sol, that will be studying in detail in the next method. Right now you have to learn these four reactions. These reactions are asked as complete the equation in your board exams. So now we'll move to the next method. The next method is Bredix Arc Method. Now the setup of this method is as shown in the diagram. This method is generally used to make the sol of metals like copper, platinum, silver, gold, etc. The electrodes are dipped in dispersion medium, which is in most of the case water, and this whole assembly is cooled by the ice bath because there is a tremendous amount of heat generated in it. Now what happens during the process? The electrodes are made up of the metal of which you want to make the sol. Now the electric arc is generated. Because of that, tremendous heat is produced. The metal vaporizes and gets condensed into this dispersion medium, resulting in the formation of a sol, and therefore we get the sol of a metal. So these are the steps involved in Bredix Arc method. The ice bath will cool the solution as a lot of amount of heat is generated during the process. The next method is peptidation. What is peptidation? It is the process of converting precipitate into sol. This definition is generally asked for 1 mark. How we can convert the precipitate into sol? By adding a suitable electrolyte. And now this electrolyte which is added is called as peptidizing agent. The definition of peptidizing agent is also asked in your board exams. Now the question is how the precipitate is converted into sol. Suppose I have any precipitate with me, how can I convert into a sol? Here I told you that by adding some electrolyte. Now we know electrolyte will have some charge on it. For example, I am adding electrolyte XY. It will have charge on it, let's say X plus and Y minus. Now this precipitate will adsorb any one of the ion from electrolyte. Let's say it is adsorbing positive charge. Now there will be many such molecules of precipitate. And all of them will adsorb these positive charge. As a result, what will happen? As a result, a repulsion will start between them and they will start moving away from each other. They will not settle down. They will not get converted into suspension and therefore they will form a colloid. We know that in colloidal solution, the particles are neither completely dissolved nor they do settle down. This is the reason behind it. That is, the charges, they are responsible for stability of colloids. Since the charges are present on them, they will start moving away from each other and will remain in the colloidal state. So this is how we can convert precipitate into a sol. Let us take the example of ferric chloride reacting with water to give sol of ferric hydroxide. Now when this ferric hydroxide, first of all, it is obtained in the precipitate form. So we'll have many molecules of precipitate of ferric hydroxide and it will adsorb Fe plus 2 ion from FeCl3. So from FeCl3, Fe plus 3 will be adsorbed on the precipitate. So what will happen? All similar charges, they will come together and therefore they will start repelling each other. As a result, this whole precipitate will be converted into sol. So this is what the process of peptidation is. In the previous method, whatever we have studied, the conversion of arsenic, formation of arsenic sol or the formation of ferric hydroxide sol, they are the examples of peptidation. The adsorbed charge can be either positive or either negative. For example, silver iodide precipitate can adsorb minus charge. How, that we'll see later on. So we have seen the preparation method of colloids. Now once the colloid is obtained, once the sol is obtained, still it will have some impurities present in it. It must be purified and therefore now we'll discuss the purification methods. So various methods of purification of colloidal solution are available. The very first method is dialysis. The setup is known as dialyzer. The colloidal solution is taken in a dialyzer bag which is made up of dialyzing membrane, and this was put in a solution, or not solution, in fresh water. What happens during the process? The particles of the colloid, they are not able to cross this dialyzing membrane. The impurities, they will come out of this dialyzing membrane and they will be removed through this water outlet. There are two inlet, one is inlet and other is water outlet. So when the process is complete in the dialyzing membrane, only the pure sol particle will be left out and the crystalloids or the impurities, they will be removed through this process. Now this process of dialyzing is comparatively slow. To make it faster, we can carry out electric current in it by adding electrodes. So we can convert this assembly into a cell by connecting it to cathode and anode. Now in this case, the process will be called as electrodialysis. Electrodialysis is done so as to fasten the process. We can also purify colloidal solution by carrying out filtration. Now the normal filter paper, it is not suitable for filtration of colloidal solution. Why? Because the pore size of normal filter paper is comparatively large. So the colloidal particles also will pass through the filter paper, and therefore we need a special filter paper which is impregnated with colloid mixture. Or I will say colloidal solution. Now what is this colloidal solution? It is solution of 4% nitrocellulose and alcohol and ether. So the filter paper is impregnated with this colloidal mixture. Now the components of this colloidal mixture, they are asked for 1 mark. Now once the filter paper, this we'll call it as ultra filter paper. Once this ultra filter paper is ready by impregnating it with colloidal solution, then we harden it by using formaldehyde. Such filter paper can easily be used for filtering colloidal solution. When we filter colloidal solution by using this filter paper, then the impurities will be removed, and on the filter paper pure colloidal sol will be left out. That colloidal sol can be mixed with dispersion medium and we can get the sol. So that was about the purification of colloidal solution. Let us move on to the properties of colloidal solution. Colloidal solution shows a variety of properties. In that, the very first is colligative properties. We have studied in the chapter solution that true solutions, they show the colligative properties, and these colligative properties are exhibited by colloidal solutions also. What are the colligative properties? Like osmotic pressure, depression in freezing point, elevation in boiling point, relative lowering of vapor pressure, etc. But we know there is a big difference in the size of true solution particles and colloid, and therefore values of colligative properties are comparatively small as compared to that of true solution. Another very interesting property which is shown by colloidal solution is a Tindal effect. In our lower classes we have studied that Tindal effect means scattering of the light. Suppose I have taken a colloidal solution in a container. This is any colloidal solution, or I will say it is a sol, and we pass light in it. Suppose we observe it perpendicularly, that is, suppose I am observing from this view, this point, and the light is passed through the colloidal solution, then we will be able to see the scattering of light, we will be able to see the path of light, and that is what we call as Tindal effect. Among true solution, suspension and colloid, only colloids are the mixtures which will show Tindal effect. True solutions and the suspension, they do not show Tindal effect. Now the question is, why colloids show this effect? The reason lies behind the fact that the particles of colloidal, they show Brownian movement or Brownian motion. Now what is Brownian movement or Brownian motion? Suppose this is the colloid particle. Now when this colloid particle is moving, it will not move in a straight line. It will move in any zigzag direction, and this zigzag movement is what we call as Brownian movement, and due to this Brownian motion the path of light is visible. Now again the question is, why the colloidal particles show the Brownian movement? It is because of the charges present on them. Colloidal particles, we have seen till now that they are the charged particles, either positive or negative, and since all have same charges on them, they try to repel each other. When they try to repel each other, they will show this zigzag movement, that is the Brownian motion. Remember my dear students, the charge is the reason for the stability of colloids. If the charge is removed, then what will happen? They will settle down and will convert into a suspension, or I will say precipitate. If the charge is removed from the sole, then it will form a precipitate, or they will settle down. This concept is important one, and so many times it is asked for give reason question. Okay. Now since we have seen that colloid particles are the charged particles, we'll study this topic in detail now. So now we know the colloidal particles are charged particles. They can be either positively charged or they can be either negatively charged, resulting in either positively charged sole or either negatively charged sole. Now the question is, when we'll get positively charged sole and when we'll get a negatively charged sole. So the colloid, suppose we have the sole of, or let's say precipitate of, metallic hydroxides or oxides. They generally adsorb positive ion, resulting in positively charged sole. On the other hand, I will use the word precipitate. The precipitate of halides, or let's say sulfides, they generally adsorb negatively charged sole, resulting negatively charged ion, resulting in negatively charged sole. Let us take one example of this. We have seen that the precipitate of FeOH3, they adsorbs Fe plus 3. So now this has formed a positively charged sole. On the other hand, silver iodide, it will adsorb iodide, forming a negatively charged sole. The sole of arsenic sulfide adsorb S2 minus, resulting in negatively charged sole. So these can be either positively charged sole or negatively charged sole. Now the question, this is a general statement. It is not hard and fast rule that only this can be there. There can be a lot of exceptions also. But on a general note, we can say this rule. Okay. Now the question is how we can decide that which ion will be adsorbed by the precipitate. Because in an electrolyte, there will be both positive as well as negative ion. So this method by which the precipitate adsorbed any particular ion is called as preferential adsorption. Now that means what? That means only that ion will be adsorbed by the precipitate which is common to both. So now we will discuss the example of preferential adsorption and we'll try to understand in detail how this process takes place. We'll discuss one very simple reaction. Silver nitrate reacting with potassium iodide to give silver iodide precipitate and potassium nitrate. This can be done by either adding potassium iodide to silver nitrate or silver nitrate to potassium iodide. You may think that whether we carry out addition of potassium iodide to silver nitrate or vice versa, both are one and the same thing. Both are not one and the same thing. Both will result in different type of sole. Now when we are adding potassium nitrate to silver nitrate, obviously there will be a precipitate of silver iodide. Now what is the common between the precipitate and this dispersion medium? It is the silver ion. So on this precipitate, silver ion will be adsorbed. So the common ion is adsorbed. Ultimately, this will result in positively charged sole. On the other hand, when we are carrying out the reverse reaction, that is when we are adding silver nitrate to potassium iodide, again obviously the precipitate of silver iodide will be formed. Now what will be the common ion between these two? Iodide. So here the adsorption of iodide ion will take place. And as a consequence, it will form a negatively charged sol. So in both cases, we get different type of sol. Now since a layer of charged particle is adsorbed on the precipitate, it will try to attack the oppositely charged ion from the solution. For example, in this case where iodide is adsorbed, it will try to attract potassium ion. So there is a double layer formation on this, like silver iodide, okay, and there will be iodide adsorbed on it as well as potassium will be adsorbed on it. So this layer, we'll call it as a double layer. The name of this double layer is Helmholtz electrical double layer. Now in this double layer there are two components. This is the first layer and this is the second layer. So the first layer is called as a fixed layer and second one is called as a mobile layer. The definition of Helmholtz electrical double layer, it is asked for 1 mark in your board exams. Now since there are two different charges present on that sol, therefore it will develop a kind of potential, and this potential which is developed, it is called as electrokinetic potential or zeta potential. The definitions of all these Helmholtz double layer, electrokinetic potential layer, they are important one. So what is the main thing? That the precipitate will adsorb preferentially a common ion from the solution, resulting in either positively charged sol or negatively charged sol. Let us discuss one more example. Next example is the one which you have already discussed 2-3 times, that when ferric chloride is treated with hot water, then we get a positively charged sol of FeOH thrice, because FeOH thrice, it preferentially adsorbs Fe plus 3. On the other hand, when FeCl3 is added to sodium hydroxide, then OH minus ion get adsorbed and we get negatively charged sol. I can write the double layer in the form of Fe2O3 dot XH2O and it absorbs OH minus ion. So these are the two different cases where we'll get, in one case positively charged sol and in another case negatively charged sol. Now let us move on to the next property. Now continuously we are giving the statement the colloid particles are charged particles. How can we prove the existence of the charge on the colloidal particles? It is through the experiment of electrophoresis. It is done with the help of an apparatus as shown over here, and the colloidal solution is filled in this. When the electric current is passed through them, suppose we have taken the positive sol, it will move to the oppositely charged opposite electrode, that is the negative one. Suppose we are taking here the negatively charged sol, then it will move to the opposite one, that is positive one. This shows the presence of the charges on the colloidal particles. Now here I have mentioned one word, coagulation. What is meant by coagulation? We are going to study that now. The next property of colloidal solution is coagulation or precipitation. Once the charge on the colloid particles, if they are neutralized, what will happen? Since the charge are neutralized, they will settle down, they will convert into precipitate. And that is what we call as coagulation or precipitation. Process of settling down of colloidal particles is called as precipitation. It is just the reverse of peptidation. In peptidation, what we have seen? The precipitate is converted into sol. Whereas in coagulation, what happens? The sol is converted into precipitate. Okay. Now, what are the different methods by which we can convert the sol into precipitate? The first one, by electrophoresis, which we are discussed just now. That the charged particles will move to oppositely charged electrode and there gets then neutralized and will settle down. The second is by mixing two oppositely charged sol. When we mix equal amount of two oppositely charged sol, the charges get neutralized obviously. For example, just now we have seen that ferric hydroxide is a positively charged sol and arsenic sulfide, it is a negatively charged sol. If we mix equal amount of these two, precipitation will take place. So this is how we can neutralize the charge on the colloid particles. The next method is by boiling. What happens by boiling? Due to continuous boiling, the adsorbed layer on the colloid particles, it gets disturbed. As a result, it will reduce the charge on the particle and therefore ultimately result in the settling into precipitate. The next one is by persistent dialysis. If we carry out dialysis for a long time, then what will happen? Whatever the traces are there in the electrolyte, we have taken the dispersion medium also there in the form of electrolyte. So that traces of electrolyte in the sol will be removed. The charges will get neutralized and they will settle down into precipitate. But the most important one is by addition of electrolyte. This we have seen earlier also. If we add any electrolyte to precipitate, it will convert into, if we add any electrolyte to sol, it will be converted into precipitate. Addition of excess of electrolyte to a colloidal particle, it will result into precipitation. Why? We know colloidal particles, they are charged one, and we are adding electrolyte to it. Electrolyte will also have some charge, either positive or negative or both. So they will neutralize the charge present on the colloid, ultimately resulting in the formation of a precipitate. Now the question is that which electrolyte can we choose? Is there any correlation between the charges present in the electrolyte and the colloid? So that answer was given by a scientist called as Hardy, and along with that Hardy-Schulze. So we'll study now Hardy-Schulze rule. Hardy-Schulze rule have given a very simple rule to determine or to choose the best electrolyte for coagulation. He said, greater the valency of flocculating ion, greater is the power of coagulation. Flocculating ion means the ion responsible for neutralization of charges. That is the ions present in the electrolyte. And that power will be called as flocculating power. So he said, as the charge on the flocculating ion increases, the coagulation also increases. Let us have one example. Suppose I have a negatively charged sol with me, and I have an electrolyte containing aluminium, magnesium and sodium. So which electrolyte will be best suitable for converting this negatively charged sol into precipitate? It will be aluminium, because of the more charge present on it. So aluminium will have the greatest flocculating power as compared to magnesium. Magnesium will have more flocculating power as compared to sodium. Similarly, if I want to coagulate a positively charged sol, then I can choose any one of from FeCN6 4-, PO4 3-, sulfate or halide. Now the question is, which one can I choose? Hardy-Schulze helps me to get the answer. Greater the charge, greater will be the flocculating power, and therefore FeCN6 4- will be the best electrolyte for coagulating the positively charged sol. Now all these methods of coagulation, whatever we have discussed, they are basically for lyophobic sole. Like we have studied for electrophoresis, we have studied boiling, we have studied this coagulation, that is by addition of electrolyte, etc. So whatever methods we have discussed for coagulation, they are basically for lyophobic sole. Why? Because the lyophobic sole, they are not stable one because of the poor interaction between them. So they can be easily coagulated by using any two of the methods. How can we coagulate lyophilic sole? The lyophilic sole can be coagulated by addition of electrolyte and by adding some suitable solvent. But before that, we have to remember that lyophilic sole, they are quite stable one. And why they are stable? Because of the charge present on them and their solvation property. Now once we remove the charge and the solvation property, then only we are able to coagulate the lyophilic sole. So in today's video, we have discussed the preparation of colloidal solutions, the purification of colloidal solution, and the properties. Today's topic is very important, as many a times question is asked from this whole topic in your board exams. That's all for the day. Thanks for watching. Have a nice day.